You've definitely seen the name in the headlines, right? Iron Dome. We see these dramatic images of rockets streaking across the night sky, and then these other lights rising up to meet them. But how does it actually work? What's the real science behind this famous missile shield? Well, today we're going to break down the tech of one of the world's most battle-tested air defense systems. Now, you gotta understand, this system wasn't built to stop some giant intercontinental missile. Nope. It was born to solve a very specific, very constant problem: short-range rockets, mortars, and these days drones, often fired at civilian areas. It went live back in 2011 with one clear goal: to create a protective umbrella over towns and cities that were facing constant, close-range attacks. And busy is an understatement. According to its developers, since it was first switched on, it has successfully intercepted threats over 5,000 times. Just think about that number for a second. That is a staggering track record built over more than a decade of pretty much nonstop operation. So first things first, let's get one thing straight. Iron Dome is not some giant sci-fi force field covering an entire country. It's actually a complete integrated system. You should think of it less like a wall and more like an incredibly smart, incredibly fast-reacting network. A single unit is called a battery. There are about 10 of these batteries positioned strategically. Now, each one has a powerful radar, a command and control center, that's the brains of the outfit, and 3 or 4 missile launchers. And each of those launchers is holding 20 interceptor missiles, called Tamir. All of those pieces working together are what create that protective net over populated areas. All right, so how does it actually do it? How do you stop a speeding rocket in midair? Well, it's a lightning-fast 4-step process. A kind of high-tech dance that goes from detection all the way to destruction. Okay, here we go. 1. The radar detects an incoming rocket and starts tracking its flight path. 2. The brain of the operation, the battle management and control unit, does some crazy fast calculations to figure out exactly where that rocket's going to land. And this is the crucial part. If it's headed for an empty field, the system does nothing. It saves its very expensive interceptor. But if it's threatening a populated area, it moves to step 3. It launches a Tamir Interceptor. And 4, that interceptor uses its own onboard sensor to get super close to the target and destroy it safely in midair. The system's eyes are this incredibly powerful radar, the ELM 2084. This thing can spot threats from up to 100 kilometers away, and, get this, it can track over 1,100 targets at the same time. This is the hardware that makes that critical first step even possible. And this is the bullet that's designed to hit the incoming bullet. The Tamir Interceptor is an absolute marvel of engineering. It's over 9 feet long, and it travels at Mach 2. That's twice the speed of sound. It even has its own little electro-optical sensor on board to make those tiny last-second adjustments. And its warhead doesn't even need a direct hit. It has a proximity fuse that tells it to explode when it's close enough, ensuring it takes out the threat. But as you can probably guess, this level of protection comes at a very steep price. And that brings us to the core economic challenge of the whole system, something called asymmetric warfare. You see, the whole philosophy here isn't to just shoot down every single rocket that gets fired. It's about being smart. Its so-called cost-effectiveness comes from that intelligent target selection we just talked about. It only uses its very expensive ammunition on the threats that are actually dangerous. And here's the core of that asymmetry, laid out plain and simple. On one side, you have relatively simple, low-cost rockets, and on the other, you have the super high-tech, incredibly expensive Tamir Interceptor that's designed to stop them. The numbers here are just staggering. An attacking Qassam rocket can cost as little as $800 to make. The Tamir Interceptor sent to stop it, around $50,000. That is the economic imbalance in a nutshell. But cost to defend is just orders of magnitude higher than the cost to attack. But despite that high success rate, the shield isn't perfect. It's not impenetrable. So let's talk about the system's limitations and why some rockets do, in fact, make it through. You always hear this figure: over 90% effective at stopping the rockets it chooses to target. So that begs the question, why does it ever fail? What's happening in those cases where a rocket actually gets through? Well, there are really 2 main reasons. The most common one is actually by design. The system calculates the rocket is going to land harmlessly in an open field somewhere, and it intentionally doesn't fire. But the second reason is saturation. If an overwhelming number of rockets are fired all at once, the system can simply be swamped, unable to engage every single threat at the exact same time. So to deal with these limitations and all the other types of threats out there, Iron Dome doesn't operate alone. It's actually just one piece, one layer of a much larger multi-layered defense network.
Think of it like a stack of nets, each one with a different size mesh. Way up at the highest layer, you have the arrow systems, designed to stop huge threats like long-range ballistic missiles. In the middle, there's David's sling, which handles things like medium-range and cruise missiles. And then, down at the lowest level, you have Iron Dome. That's the fine mesh net, catching the small, short-range stuff. Each layer has a very specific job to do.
Now, this entire setup isn't static. It can't be. It's constantly evolving because defense technology is locked in this perpetual arms race with offensive technology. Each side is always trying to get one step ahead of the other. And a huge part of that evolution is trying to tackle that cost problem we talked about. So enter the next major addition, Iron Beam. It's a high-energy laser system, and the cost difference here is nothing short of revolutionary. You go from $50,000 per shot for a missile down to just a few dollars worth of electricity to fire the laser. But the laser isn't a silver bullet. While the cost is a massive, massive advantage, it comes with trade-offs. It has a slower rate of fire, it has to focus on one target at a time, its performance can be hampered by bad weather like clouds or rain, and its range is a lot shorter. This means it will almost certainly work alongside missile interceptors, not replace them completely. And this leaves us with a fascinating final question, doesn't it? In a world where offensive weapons just keep getting faster, smarter, and cheaper, the defense is always playing catch-up. It raises this fundamental question about this technological arms race. Can a shield ever be truly perfect?